Hello dear friends, welcome to my channels. Today's discussions first order non-degenerate perturbations theory. So friends, we need to know what is perturbations theory, why do we start the course with it. We will discuss exactly how to use it, but we can use it whenever we have to have a small perturbation to the Hamiltonian. This is my Hamiltonian and this is my unperturbed Hamiltonian and this is my small perturbations. So, so for example, we are going to have our Hamiltonian which will be comprised of, let's say, for example, this could be H0. What we call unperturbed Hamiltonian. This is unperturbed perturbed Hamiltonian. And that's going to be, for example, the Hamiltonian of the infinite square will on the Hamiltonian. For maybe the harmonic oscillator or whatever Hamiltonian you want, and to this Hamiltonian which we already know, we are going to add a small perturbations in right. Yeah, you see that this is going to be small in comparison to the normal Hamiltonians. That's why we can use perturbations theory. If this perturbations means was really big, we could not treat it as a upper turbines, because the whole of this is that, for example, we are going to have as we will. So this kind of spoiler, we have the infinite square well. Okay, this is the infinite square well, and then we add maybe just a little bump. Important key thing to understand about the perturbation theory is that this is an approximation. Okay, so sometimes we will be lucky and our result will be the, that is not going to be the case of general. Many times we will have an approximate result which will be very good, especially for the energy state perturbations theory. In quantum mechanics is quite good at calculating the energy levels, but not all that amazing at calculating the wave functions. We are making somewhat of the sacrifice here, but considering that the problem would be much harder to solve. Otherwise, this is still pretty good. Okay, and why exactly do we care about this, and why do we learn in quantum mechanics? We discuss hydrogen atom and spin. Okay, hydrogen atom and spin, please check my videos. I have already created hydrogen atoms. Okay, I try to give a link in this video, then you can easily, otherwise please check my playlist where I created hydrogen atom and spin half also. So the hydrogen atom has actually quite a few effects that we didn't reality take into account. For example, there is an electron and proton, which will be attracting each other, so that movement of the electron is actually going to be around the center of mass. We didn't really account for the mass of the proton at all. Last time we also didn't take into account the fact right, that the movement of the electron will produce a magnetic field. The electron and the proton on that fact right, that the movement of the electron will produce a magnetic field that is going to produce other coupling between the spins. So there are a few concepts that we didn't take into account, and the reasons was that it didn't make that much of a difference. If we really want to more accurate, we should consider those as well as, for example, some relativistic effects. So the way to do that without having to just refocus everything as we do in relativistic quantum mechanics, which we will see a little bit of in the start of the quantum field theory course. Well, without having to change everything, we can use perturbation theory, and it also good to discuss perturbation theory because it's very important in quantum field theory, right? So first order non-degenerate perturbation theory. Example, hydrogen atom. And why first order? Because we can take many orders to increase precision and just un. So friends, again I just write H psi equals to E psi. Hamiltonian is comprised, as we just saw, of some unperturbed Hamiltonian. H equals to H0. This is the unperturbed Hamiltonian, and add some perturbations. Perturbations means lambda H dash, to help us know that H bar is going to be small in comparison to H0. H bar, this is the H bar is 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 going to be small in comparison to H0. The unperturbed Hamiltonian, but as we will see, the lambdas will end up dropping out. So this is mainly there is psi n is equal to psi n 0 plus lambda psi n 1 plus lambda psi n square. This is the first order correction. This is second order correction. so on so forth. And of course the same thing goes for wave functions. For now we do not really care about higher order, so we can write it in this way, that E psi is equal to h plus lambda h dash, okay, h0, sorry, not h0, 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 okay, this portion I am just putting this value and this value is just multiplying in here, okay. So h0 plus lambda h dash is equal to psi 0 psi n 0 plus lambda psi dash n plus lambda psi n square, okay. Similarly, okay, it is not lambda square, is very lambda square, it is second order, so it is lambda square, okay. Similarly we get e0 e0n plus lambda e1n plus lambda square en square, and psi n lambda psi n plus lambda square psi 1 psi 2 n. Now we have to do little bit of tedious work. Just multiply each. So what I get, h0 psi and n0 both are unperturbed unperturbed perturbed perturbed Hamiltonian or unperturbed function wave functions, and lambda h0 psi n1 plus lambda square h0 psi n whole square plus lambda h1 psi n0 equals to plus lambda square h1 psi n1 and en0 psi 1 n plus lambda en0 psi n1 plus lambda square en psi square n plus lambda en1 psi n plus lambda square en1 psi n1 plus lambda square en square psi 0 n, okay. Now we so friends we need to take first order, okay. So our first order portion is lambda 1 h0 psi 1 n n, and h bar, yeah, h1, h bar, okay, h bar psi 0 n equals to e 0 n psi 1 n plus e 1 n psi 0 n. Okay, we can similarly we can calculate also second order second order 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 second order. Okay, so second order collections we can easily find out, but I don't need, because I need to find out first order, because my discussions topic is first order. Second order I will publish my next video. You will check my next video. There you can get these values. So friends, this is my equations, this is my important equations. Okay, this equations is very important. Okay, I hope it is clear. This equations is very important. Now, since we are going to be delaying with normalized states, this should be equals to 1. Our goal, which is to find on our target, may be, which is this: en1 will be isolated, and that's why we want to use this trick. And of course we want to use the notation of brackets, bra psi and zeros. Okay, let's do that. So here on the left hand side we get psi 0 ends. So left hand side I just multiply bra psi n psi 0 multiply bra psi n zeros. So if I multiply with these equations, bra then psi 0 n and okay, lambda 1 is not, lambda 1 is cancelled because the first order, so lambda 1 may be cancelled. Okay, no problem. This is the, yeah, so psi 1 and psi 1 n. Okay, psi 0 n 0 n and psi n 1, this way can be written h0 psi 1 n plus psi 0 n h bar psi 0 n equals to psi n 0 e n 0 and psi n 1 plus psi n 0 e 1 n and psi 0 n. Okay, now let us take a look at each one of these components. Very important Hamiltonian property. Hamiltonian we call as an observable able, we apply it has to be Hermitian, its complex conjugate, and since it is complex conjugate, since it is Hermitian, so this portion is going to 1. So I get, okay, I can write this way. I get this value is equals to, this value is equals to E dash n, because both are 1. This is the Hermitian matrices, so I get this E n. Okay, so clear. I hope it is clear for everyone that how it is coming, because please check my first video where I discussed bracket etc. So it has to be Hermitian. So now H0 psi n0 psi dash n, can how it is en, this you will check. Okay, psi dash n equals to E0n E0n psi n0 psi n1. Okay, now you have to must remember H0 psi n0 equals to E0n psi n0, and unperturbed energy, unperturbed state, so they are not necessarily orthonormal. So let's continue them this. So H0, so this portion and this portion can be written this way, that this equation, this is my equation, this is my equations. Okay, okay, this is my equations. Now I can write that E n0 psi n0 psi n1 plus psi n0. Okay, from these equations you get in here h dash, sorry, it is h dash psi. That implies my equations is going this way, that psi n0 equals to E n0 psi n0 psi dash n plus E n1. So friends, this portion I can cut this portion. Okay, this portion and this portion is cut. Okay, so what we get E n1 equals to psi n0 h bar psi n0. Okay, first order corrections. This is the first order corrections for. Okay, 1 minute. 1 minute. I think there is some mistakes. Okay, psi 0 1 psi 1n psi 0n. Okay, psi 0n h bar perturbations is in here. No problem. So first order corrections of non-degenerate perturbations theory is simple on this is supposed to be h prime, means h prime or h bars. Okay, energy is going expectation value of a perturbance with respect to unperturbed wave functions, unperturbed wave functions. So psi n1 can be written as m does not equals to n c m n psi 0 psi n1 1 equals to summation m does not equals to n m to n psi m 0. Here m is the linear, by taking linear combinations, m is the index that denotes the linear combination of the unperturbed state. Okay, that we are using and relates to at least the state that we want to find the first order corrections. And psi n1 psi n1 equals to summation m does not equals to n c m n psi m 0, and psi n equals to psi n0 plus lambda psi n1 plus lambda square psi n square. The same then the term contained up to p psi 0 0, which is already there since the wave functions are not normalized. It does not really make sense to have a second term. Okay, it does not make this this term is the psi n 0. So first order corrections. So H0 psi n 1 plus h, yeah, h bar, yeah, h bar, okay, h bar psi n 0 equals to e n 0 e n 0 psi n 1 plus E n1 psi n0. So H0 minus En0 psi n1 equals to minus H bar minus E1 n psi n0. In this equation, I will now put the expressions that we wrote for this, the psi n1. So H0 minus E n1 is putting the value summation m does not equals to n c m n and psi 0 n 0 equals to minus h bar e1 n psi n0. The unperturbed energy states are the ones that we usually already. The problem is that our coefficients are stuck inside of a sum. How do we get rid from the sum? These states are the orthonormal. These states are the orthonormal. These states is orthonormal. So if we can somehow get a state that is, for example, psi n0 and psi m0 equals to del n m, okay, equals to del nm. So because it is normalized, multiply it left by this bra, all rights. That's our goal here. So multiply psi L0 bra psi L0 multiplying, so I get H0 minus E n0 summation m does not equals to n c m psi equals to minus psi L0 h bar minus E1 n minus psi 0 n. And this is the value. You have to remember that this is so we are going to get this value. So this value is, you get psi L0 H0 this way, can get E L0. So we are going to get this value. So we can write this way: psi L0 E0 L minus E n0 summation m does not equals to n cm n psi m0 equals to minus psi l0 h bar minus e bar n psi 0 n and el 0 minus e 0 n summation m does not equals to n c m n psi l0 divided by psi n0 equals to now different from nth coefficient are also numbers, so we can just pull them out as well and we get the bracket between psi 0 and this portion can be written as del ln, so it is this portion can be written as del ln. Okay, so you can write this equation summation psi l0 h prime psi n0 minus plus psi l0 prime h prime psi n0. So friends, this is the del ln. So del ln, so this portion can be, suppose l equals to, this portion kills the condition, so what we get, the summations will be vanished with the Kronecker delta. So we get e l0 minus e n0 and this portion can be written as c mn equals to minus summation psi l0 plus h bar psi n0 plus e n dash psi l0 and psi n0, the wave functions. So this is also del, it is also del ln and suppose l equals to m equals to n, this is the breakdown, and L equals to n and L does not equals to n. So if L does not equals to n, then it is 0, and this is the possibility L does not equals to n as n equals to m we have already considered. So it is the possibility that L does not equals to n, so it is 0. So whatever we get E L0 E 0 n C m n equals to minus psi L0 H1 H bar H prime psi n0. Okay, psi n0. So cnm, so cnm equals to psi L0 H prime psi n0 and divided by E L0 minus E0 L. This is n. This value is n. Okay, so I am putting this value. So whatever I get psi 1n equals to summation m does not equals to n psi m 0 h bar h prime psi n0 divided by e n0 minus e, it is bracket, and psi 0 m, because I have already told that what is the psi L0. This from this formula I get this value. Okay, I get this value from these equations. Okay, I have already mentioned this in here, so you get this. So thanks for watching, friends. I hope I can give some ideas, and I will discuss in my next video.